Today we will begin discussion of magnetism, a fascinating phenomenon of nature that is as widely spread and important as electricity. Electricity and magnetism are two fundamental types of physical forces. They often appear together, but as we will see, magnetism is quite distinct and is not the same as electricity. In the previous lectures, we discussed electric force occurring whenever a body carries an electric charge. Any two small charged objects, A and B, will interact through an electric force described by the Coulomb's law. This force is directed along a line connecting A and B. It is always present if both charges are non-zero. The force exerted on B is related to the force exerted on A by the third Newton's law. To describe more complex configurations of charges, we introduced the concept of electric field. We also derived equations that describe electric field. We introduced the concept of electric potential, which is very handy in many calculations. Now, for centuries people knew that there is another type of force that can be similar to the electric force, but clearly is not the same. Its exact nature eluded humans' understanding until about 150 years ago, when scientists established exact equations that govern it. Just as the electric force, this new force occurs between a pair of electrically charged objects. However, in contrast to the electric force, the magnetic force is only present when both electrically charged objects move. For instance, consider again two point-like charges. The velocities of both charges must be non-zero for their magnetic interaction to happen. Even if one charge is at rest, the magnetic forces are absent. The other peculiarity is that the magnetic force always points in the direction that is perpendicular to the velocity of the charge that feels it. So you can see from the figure that each charge experiences a magnetic force that is perpendicular to its velocity. This is quite bizarre, but has been confirmed experimentally. And, of course, the third Newton's law generally does not apply to the magnetic forces exerted on the charges. They do not have to be opposite to each other, as the electric forces are. This is the totally new type of force, the magnetic force. We will study it in the course of the next few lectures. Although magnetism and electricity are interconnected classes of phenomena, they were thought to be independent for an extended period of time. Nevertheless, electric and magnetic forces always appear together. We will learn a little later that separation of electric and magnetic forces depends on the reference frame. If in one coordinate system there is an electric field but no magnetic field, then in a different coordinate system that moves with respect to the first one, both electric and magnetic fields will be non-zero. Only the combination of electric and magnetic fields is invariant in all coordinate systems. Humans knew about magnetic forces for thousands of years. Certain materials, known as permanent magnets, create magnetic force around them for very long. For example, iron ore found in nature can sustain permanent magnetization. Ancient Greeks knew about it long before our era. They knew that iron rocks, called lodestones, can attract objects made of iron and iron alloys. Such attractive rocks got the name of magnets after the geographic area of Magnesia in Greece, where such rocks were commonly found. Since very early, the Greeks realized the differences between electric and magnetic effects. Thales of Miletus, who lived around 600 BC and is considered to be the founder of Greek school of natural philosophy, contemplated about differences between the electric force created by rubbing amber and magnetic force exerted by a lodestone. In China, magnetism was known since about the same time or even earlier. Compasses made of a magnetized metal in the shape of a spoon or fish were employed for magic rituals and navigation. During all this time, people had a wrong notion that permanent magnets are made by northern and southern magnetic charges tied together, similar to electric dipoles. This notion turned out to be wrong. By now we know that magnetic charges do not exist. Rather, we've learned in the course of the last 2 centuries that magnetism is closely linked with electricity. One of the key breakthroughs happened in 1819 when a Danish physicist, Hans Christian Ørsted, discovered that a magnetic field can be created by an electric current. In the 1850s, an Englishman, Michael Faraday, found an opposite effect, that changing magnetic field will create an electric field. About a decade later, another Englishman, James Clerk Maxwell, determined 4 fundamental equations describing transformations of electric fields into magnetic fields and the other way around. A notion of universal electromagnetic force was introduced. Yet another advancement happened at the beginning of the 20th century, when Albert Einstein demonstrated that electromagnetic interactions exist as a consequence of fundamental symmetries in nature, predicted by his theory of special relativity. So how does the magnetic force compare to its electric counterpart? Some students studying the magnetism are pleasantly surprised when they realize that equations for the magnetic fields can be reminiscent to the electric field equations. By their general look, the equations for the magnetic field and magnetic force are similar to the Coulomb's law for the electric field and the equation for the electric force. Since the overall structure of the equations for electric and magnetic fields is about the same, it is easy to memorize them. But beware, the analogy between electricity and magnetism is not perfect. There is one striking difference that affects all equations. When we studied equations for electricity, we learned that electric forces and electric fields are always proportional to electric charges Q. In contrast, equations for magnetic forces and fields are always proportional to electric charges multiplied by charges velocities, Q times V. That is, essentially, they are proportional to electric current I. No magnetic charges exist. Electric currents are the only source producing magnetism. Magnetic force does not propagate through space instantaneously. Just as the electric force is mediated by disturbance of space-time, called electric field, the magnetic force is carried by another kind of disturbance, called magnetic field, and denoted by letter B. There are a few properties of B that you wish to remember. Mathematical equations reflecting these properties will be worked out later in the lecture. First, any moving charge creates magnetic field B around it. Second, any moving charge inside magnetic field feels magnetic force. Magnetic fields obey the principle of linear superposition. If there are n moving charges, each creating a magnetic field, the total magnetic field of all charges is simply equal to the sum of individual magnetic fields. How do we know that the magnetic field exists on its own? How do we know that the magnetic field B, which I described to be a disturbance in space, is a real thing? Can it exist independently of the charges? The answer is yes. When B is present, it reveals itself not only through the magnetic force on moving charges, but also through a variety of other effects. For instance, B can rotate a compass needle, magnetize iron or other ferromagnetic material, or change frequency of light emitted by atoms. These effects grow weaker or stronger when B is varied. We can even select one stable effect and use it to measure strength of B. For instance, we can measure strength of B by measuring torque on a small magnetic needle in the region filled with B. In the International System of Units, the strength of B is measured in teslas. By definition, 1 Tesla is equal to 1 Newton divided by Coulomb per meter second. 1 Tesla is a very strong magnetic field. Only the largest electromagnets can create a field of order 1 Tesla or more. In applications that do not consider such strong magnetic fields, another unit is often encountered, 1 Gauss. By definition, 1 Tesla is equal to 10,000 Gauss, so a small bar magnet will have a magnetic field of order a few Gauss. Magnetic fields in the environment around us vary in a wide range, but very rarely we encounter fields that are stronger than a few hundreds of Tesla. Permanent magnets present the most common source of magnetic force. Typically, permanent magnets are made of magnetized iron or other materials that produce constant magnetic field around them. As I already emphasized, magnetic field is always created by electric current. In the case of permanent magnets, magnetic field is created by tiny electric currents that circulate at the atomic level. In each atom, electrons moving in orbitals around the nucleus create a persistent microscopic current and in turn create a tiny magnetic field. In a non-magnetized material, atoms are not aligned. Their microscopic fields essentially cancel out. Unmagnetized materials have no net magnetic field. But under some circumstances, all atoms inside the material are aligned, so that their microscopic fields add up. This causes permanent magnetization. The total magnetic field that is created is the strongest at 2 points on the objects, called the poles. The poles are special points on a magnetized object and not magnetic charges. At the North Pole, the magnetic field is directed out of the object. At the South Pole, it is directed in. If we bring together two magnetized objects, their poles of the opposite polarity attract, north to south and south to north, and the poles of the same polarities repel, north and south and south. Earth also has a permanent magnetic field. The south magnetic pole of the Earth is located close to the north geographic pole. The north pole of a compass needle is attracted to the south magnetic pole of the Earth and approximately points towards the geographic north. Magnetic field of the Earth is created by large-scale currents of electrically charged material in the rotating Earth's core, which can persist for thousands of years. From time to time, convection currents in the Earth's core change direction, causing the magnetic field of the Earth to flip or even totally disappear. Electromagnets, or solenoids, have been invented to create artificial magnetic fields. A typical electromagnet is made of a large number of wire loops wound on a cylinder. When electric current passes through the wires, it creates a strong magnetic field. Often, an iron core is inserted inside the cylinder to increase the magnetic field by a factor of a few hundreds or thousands. Electromagnets come in a variety of sizes and strengths. They are encountered in car starters, imaging units of hospitals, in science and industry, and many other places. The strongest magnetic fields exert enormous force on any object in their vicinity, including electromagnets themselves. As a result, it is difficult to create a magnetic field stronger than about 100 Tesla, as the electromagnets that create it experience strong mechanical stresses that eventually destroy them. Electromagnets are widely used to create artificial magnetic fields. For example, in the Large Hadron Collider, a variety of electromagnets are controlling flow and collisions of charged particles accelerated to nearly the speed of light. Colliding particles are detected at the LHC by a device called the compact muon solenoid. This is nothing but a huge electromagnet with about 7 meters in its radius. Inside the compact muon solenoid, very strong electric currents in superconducting cables create two regions of very powerful magnetic fields with strengths of about 4 and 2 Tesla. The strongest magnetic fields that are ever created by humans can reach about 1000 Tesla. These fields are so strong that any device that creates them is destroyed in an instant. The devices that create pulses of strongest magnetic fields are called exploding magnets. In the photo you can see how the exploding magnet operates. After a strong current is created in the magnet, a huge tension force breaks apart the material of the magnet. It explodes in a bright fireball. Ultra-strong magnetic fields can have many applications. For instance, in fusion reactors, very strong magnetic fields can hold plasma that can produce essentially unlimited source